this is just a plot that shows how the fin efficiency relates to the fin constant. So, it's important to kind of sort out what we mean by an ideal fin, right? We've said that an ideal fin is where the entire temperature of the fin is at the base temperature. Okay, so if that's the case, it's really small ml. It's very easy to move heat. The entire fin is going to be perfectly at the temperature that's at 1, right? So now, as you make the fin longer and longer, essentially, heat has a harder and harder time making it to the end, and you're adding extra area that's really not fully being used, right? It's not fully at the base temperature. So that fin efficiency drops down and you sort of tail off as you go. Okay, so we'll look at ease in just a second. Any questions on this? No? Okay, so let's look at ease here. See if I can find it. So if you wanted to look at ease and come up with a, look at a given geometry, you can go to the function information. So that's options function information. You can go to heat transfer and fluid flow. And then you can go to, where is it? Fin efficiency, right? So fin efficiency. And then there's a whole library of things you can look at. So this is the one we just did, right? This rectangular fin. And then you can flip through, like, okay, you've got these different options, weird shapes that you might see, right? There's all these are here. Actually, next we're going to be looking at this example. But yeah, these are all here. And then you also can look at things like dimensional efficiency versus non-dimensional. So if we were to do non-dimensional, you'd actually have to manually calculate ML. Right? You calculate ML and then you give it to the function, and it calculates that fin efficiency. The other thing you might find useful is, let's look at something like this. So if you go to info, it'll always tell you how to calculate the area and kind of what the parameter is. So if you're ever confused about what's my fin parameter or what's the area I should be using, you can look at the library function. It'll give that information to you. Okay. All right. Let's see. Let's go back here. Cool. Yeah. So here's our little summary of. Where'd that go? Yeah. Here's summary of the tables. So that should be in there. All right. Last thing on this before we do another quick example would be. So we've talked about this fin efficiency concept, right? This is the solution we just came up with. This one here. More or less. What if we have a bunch of fins that are mounted to a plate like this? So now, do we have to go through and calculate the fin efficiency for one fin or for the whole array, or kind of how does that work? So to deal with stuff like this, and actually just in general, something that's useful is to define something called a fin resistance. Okay, a fin resistance is really the same kind of concept we've been talking about for resistance. Thermal resistance, but let's kind of hash it out here. So let's write out our heat transfer rate. So that would be, so let's say I've calculated my fin efficiency. How can I write the rate of heat transfer? We just write it as Q dot fin is equal to eta fin times H bar A T B minus T infinity, right? This is just rearranging this equation above it. Once you go to the trouble of computing the fin efficiency, you can solve for the heat transfer this way. Okay, so this actually looks a lot like, this here kind of looks a lot like a resistance, right? Kind of what we've been doing before. So actually, we just have this fin resistance come out of this. That is our fin is equal to 1 over H bar times A, right, times eta fin, right? That's now our fin resistance. It's essentially a convective resistance. It's the same thing as a convective resistance, but it's scaled by the inverse of this fin efficiency, right? Fin efficiency is always between 0 and 1. It's a number between 0 and 1. You can't possibly physically have a number for fin efficiency outside of that. If you could do that, you'd be a very rich person. Right? But those are the physical limits on it. So what is that saying? Well, our fin, if it's a perfectly efficient fin, eta fin is 1, then it's just the same as saying, I'm going to take that full surface area, put it at TB, that's my resistance. If it's less than 1, then our fin goes up, right? It becomes harder to get heat through that fin than it would if it was an ideal fin at TB entirely. Okay, so this fin efficiency is almost always going to be increasing the actual resistance compared to that full surface area if it's fully at that temperature. Okay, so we have now our fin. This is the fin for just one of these little, right? Just one of the little fins here. So we would compute our fin for one of those fins. And now in this fin array, we can use that resistance concept and repeat it to come up with a total effective resistance. So how would we write total resistance for this array? So our total, right, so our total is going to be, so maybe it would help to kind of draw a diagram. So let's say we have TB here. This is our base temperature. And heat's trying to get from the base down here out to the surroundings at what we call it T infinity, right? T infinity here. So it's trying to get out. What are the different ways that heat can flow? Well, heat could flow, it could flow through, oops, weird. Heat could flow through the first fin, our fin 1, out to T infinity. It could flow through our fin 2, right, out to T infinity, and so on, right? I don't want to write out 70 of those. The other thing that's important though, right, this continues. The other thing that's important is it could go through the unfinned base part of it. Okay, so he could actually flow through that right directly from the base that doesn't have any fins on it, our base to T infinity. So when you're writing out the total resistance for an array like this, you're just going to do the parallel combination of essentially, you know, you treat this here as one big fin and call it like N over R fin. And then this is going to be the resistance associated with just the base, the base area that's exposed. Okay. Does that make sense? Okay. You guys seem tired today. You're all up late doing heat transfer homework. All right. Okay, so let's do the last thing today. Yeah, go ahead, John.
My question is, can you scale the surface area 1/5 by n?
So you're asking if you made a single fin, like if you just made it really, really long, or what do you, is that?
Get that parallel surface area 1/5 by
You would, so what you want, yeah, I think you're saying essentially the same thing as we're doing here, right? So like if you take N divided by R fin, what I mean here is, let me be clear. So our total is going to be, right, 1 over R fin 1 plus 1 over R fin 2 plus so on, plus 1 over R base. Right, the parallel combination of those things. So if I have N fins that are all exactly the same, this is going to be the same as this is going to be the same, and so on. And so it just becomes N of those divided by R fin. So you essentially are scaling the area, but you're doing it by, you're doing it by just repeating that resistance a bunch of times. And when you add the inverses of them together, you're actually decreasing the total resistance.